Hello everyone, and thank you for attending this presentation. Today, I will talk about applying artificial intelligence tools such as LLMs and vision models to tabular datasets. We have touched upon this topic in our earlier presentations, and therefore, before delving into the details of this presentation, I would like to provide a brief overview of what we have done before, and this will give us some background and context for our discussions today. Most of the analysis in our data science world is done with tabular datasets. Whenever we have this type of tabular dataset, there are of course numerous established and tried and true methods for predictive modeling. Data transformation, feature selection, and modeling techniques such as logistic regression, random forest, XGBoost, etc. can all be used to generate good AUCs and accuracies for this type of data. And we tried some of these methods in our earlier experiments, and we found that these methods continue to perform well. We next asked the question, with so many advances in generative AI recently, can we harness the power of generative AI to enhance our predictive models? We experimented with several large language models and found that these models could help us in two possible ways. First, we could extract the embeddings from these models as additional variables in our logistic regression models, or we could use some of these large language models directly to enhance the predictive power of our models. We experimented with both these methods and we found that both of them improve the performance of our models as compared to the traditional modeling techniques. In this presentation, we introduce another class of models, image models. And we aim to explore whether these types of models can further improve the AUCs for our data. Why image models? Well, images are all around us. We human beings start out our lives by processing images and objects around us and become exceptionally good at it. And we end up classifying objects every day without really thinking too much about it. This is round and rubbery, so it's a ball. This object has four legs and a flat surface, so it's a table. Here is a glass of water, and that is a pen. And here is my computer. So we are really good at looking at features of images and objects and identifying what they are. Learning to understand words only come later once we learn to recognize alphabets. So our brains are wired to get a lot of information from an image, and we have all heard the saying that a picture is worth 1,000 words. Since neural network models are inspired by the structure and function of the human brain, it makes sense that neural networks would also be very good at image classification. In fact, in recent years, image classification has seen major advancements, with deep learning models sometimes achieving above human level performance in object detection and recognition. This has been possible due to convolutional neural networks, which are a type of deep learning neural networks particularly well suited for analyzing visual data like images and videos. CNNs can effectively extract information from images through convolution operations. They excel at extracting spatial and hierarchical features as well as feature interactions from images. So now that we have a neural network that excels at extracting features from images, can we utilize it to enhance our predictive models? The challenge is that our data is a tabular data set, and tabular data lacks the spatial structure that CNNs require to operate effectively. In order to use the power of CNNs, we need images. So the next challenge is to convert this high-dimensional tabular data set to images. There are many ways in which this can be done, even when we have a tabular data set with large number of rows and columns. Let me digress here for a few moments to talk about the data set that we have been working with in all of our experiments, including the current ones. We have been working with the Australian credit risk dataset, which contains approximately 14 attributes, some of which are numerical and some are categorical. The attributes were masked, and we have a binary dependent variable which identifies the defaulters. As before, all models were built to regulatory standards, so we dropped variables from our models if they were too highly correlated with the dependent or with any other independent variable. As I mentioned before, in order to use CNNs, we must convert our tabular dataset to images, and there are many ways to do so, which I will talk about next. In embedding-based methods, the actual feature value is embedded into the image. This is an example of a tabular dataset where V1, V2, V3, and V4 represent the variables and the rows represent the observations in the dataset. In the embedding-based methods, the numbers from each row are embedded into the image as shown, resulting in one picture for each row. In all of the images that we have shown so far on this slide, all the numbers are of the same size. In some versions of these embedding-based methods, more important features are allowed to have larger embeddings, as shown in this last image over here. Sometimes a representation of the feature instead of the actual feature value is embedded into the image. For instance, a byte representation of the data may be embedded into the image. We experimented with some of these embedding-based methods to create images using our Australian credit risk dataset. And we used the CNN model to train those images and obtain predictions for our validation and test datasets. We wanted first to see what would happen if we inserted a byte representation of the data into the image. The first row shows this scenario, and we can see that the model did not perform well at all, and the AUCs were quite low. Next, we wanted to see whether things would change if, instead of a byte representation of the variable, we just inserted the values of the variables directly into the image. We tried this scenario next and decided to keep all the values in the image of the same size, which means that all the features are given equal importance. As we can see, the AUCs when these images are trained with the CNN model are very high. Next, we wanted to see what would happen if we increase the font size of the more important features in the image. The third row shows this case where more important features have bigger fonts in the image. When these images were trained using a CNN, the AUCs were slightly lower. What is interesting here is that when we give the model more information about the importance of features, the model's performance declines. Less information about which features are important seems to allow the neural network model to perform better. And I will discuss more insights about this later in the presentation. Another method of creating images from high-dimensional tabular data is the permutation-based method. This method starts by using some kind of distance measure to calculate similarity among features. So in this table, F1 through Fm are the M features of our tabular dataset, and this table represents some sort of similarity measure between each pair of features. These features are then mapped to a two-dimensional space in such a way that features that are similar to each other in this table are assigned pixels close to each other in the image, whereas non-similar features are further apart in the pixel space. So the algorithm makes sure that features that are similar to each other in terms of distance are also closer to each other in the image. Each feature is represented as a pixel in the grayscale image with pixel intensity corresponding to feature values. In this slide, we show the results from our experiments with the permutation-based method. As we can see, the AUCs from this experiment are neither too high nor too low. Another tabular to image conversion method is based on dimensionality reduction. I will explain this method with an example of a tabular dataset like this one, which contains n observations and m features. The observations in this dataset are represented by rows, and F1 through Fm are the m features. Dimensionality reduction-based methods first transpose this high-dimensional tabular data so that each row corresponds to a multidimensional feature vector. So once we transpose this data set, each row corresponds to one feature, and we can say that each feature is an n-dimensional vector. Then these methods apply a dimensional reduction algorithm so that each n-dimensional feature vector is reduced to 2 dimensions. These 2 dimensions can now be treated as Cartesian coordinates in a 2-dimensional plane and plotted in a graph to create a 2-dimensional plot where each point represents one of the features. Different dimensionality reduction techniques can be used, such as principal components analysis, kernel principal components analysis, TSNE, multidimensional scaling, etc., to portray each multidimensional feature to a 2-dimensional space. This slide shows the results from several dimensionality reduction-based methods. In each of these cases, a different dimensionality reduction technique is used to convert a high-dimensional feature vector into 2 dimensions. And then those 2 dimensions are used to plot the features in a 2-dimensional space. The first row shows the results when multidimensional scaling is used. The second row shows the case where principal components analysis is used. And the third row shows the case where t-distributed stochastic neighbor embedding, or t-SNE as it is often called, is used. The last row is a slightly different case where correlations of features with the dependent variable are used to determine the position of features in the images. As we can see, most of the AUCs look reasonably good, and the AUCs shown on the last 2 rows are higher than the others shown on this page. On this slide, we present a summary of the key findings from our image modeling experiments. We have seen all of these results in our earlier slides, and they are just compiled here so that we can compare them. The first few rows shows the embedding-based methods, which means that the feature values or a representation of them are directly embedded into the image. The fourth row shows the results from our permutation-based method. This method assigns feature to pixels by minimizing the distance ranking differences between the original and image space. The next few rows are based on dimensionality reduction methods, which map high-dimensional feature data to 2 dimensions, enabling us to plot the features in 2-dimensional space. I'm highlighting the best methods with the highest AUCs in red font so that we can see that one of the embedding-based methods and a couple of the dimensionality reduction methods perform the best in terms of AUCs for our experiments with the Australian credit risk dataset. So overall, we find that these image-based models are able to extract and engineer some different types of features and relationships from our data sets that help to improve the performance of these models as compared to some of our traditional methods. And we will see this in greater detail later in the presentation. Let us next talk about some of our key observations and findings from all of our image-based experiments. Firstly, the surprising thing that we noticed in the embeddings-based models is that the models perform the best when we did not tell the model which features were more important. We saw that when we embedded the features into the image without adjusting their position or size, the model performed well. The model's performance and AUCs decreased when we attempted to identify the more important features. It's almost as if the neural network model is instructing us not to interfere and let it determine the more essential features. Usually, when we try to identify these more important features, we may be using some sort of modeling technique such as regression or XGBoost. And when we try this, we may be adding some sort of bias into the model about which features are important and by how much. The neural network model may be better able to look at the data and identify the more important features for us. In permutation-based methods, we found that these models perform okay, but the AUCs of these models were not too high in our experiments. In these methods, we usually use a distance measure to figure out which features are similar to each other. And then we control the position of the features in the image, as features similar to one another are given spots close to each other in the picture, and features that are far away in distance are also further apart in the image. Once again, our biases in our distance measures may be hurting the performance of these models. We tried several different dimensionality reduction methods, and some of them work better than others. And dimensionality reduction almost always results in some sort of loss of information, and we see that in our AUCs as well. We found that when we use t-SNE for dimensionality reduction, the model performed better than when we used multidimensional scaling or principal components analysis. This may be because t-SNE is better at capturing the more complex, nonlinear relationships, and principal components analysis is better suited to capturing linear relationships. Multidimensional scaling preserves the global relationships among data points much better, whereas t-SNE is better than multidimensional scaling at capturing the local clusters. And so, if the true relationships in our datasets are nonlinear, more complex, and local relationships are more important, t-SNE may be better able to capture those relationships. And if linear relationships are more important in our dataset, other methods may perform better. In all of this, we also have to keep computing resources in mind. For instance, t-SNE can be more computationally intensive than PCA, so when working with large data sets, we may have a trade-off between performance and computational resources. In our experiments, the simplest embedding-based method performed the best. However, in this approach, we directly embed the feature values into the image, resulting in each feature occupying significantly more space than in other methods, where each feature is represented with only one pixel. While this may be advantageous for the CNN, as it is getting more information about each feature, it also adds to the computing resources. So for large data sets, we may have to upfront decide on the more important features and then use the embeddings for only those features to create our images. On this slide, we present a summary of the key findings from all of our experiments. In our previous webinar, we performed the first experiment by directly giving a prompt to the llama model. We found that its predictions were not significantly better than those of a random guess. The traditional logistic regression model performed much better than the llama model, as shown in the second row of this table here. At that time, we were also able to extract embeddings from the llama model, and when we used those embeddings as additional features in our logistic regression model, the AUCs went up significantly. We also tried to fine-tune a more specialized LLM model, which is the Finbert model, and found that such fine-tuning significantly increased our AUCs. So the top performing models for our earlier experiments were the fine-tuned LLM, which is shown on the fourth row, and the traditional plus embeddings logistic model, which is shown on the third row in this table. Today, we have talked a lot about image models, and some of the results from our top image models are now shown on this slide. Upon inspecting these results, we find that they look even better. So our top performing image models outperform the LLM models we tried in our earlier experiments with the same dataset. We are, of course, still experimenting with both LLM models and image models, and work in this area is ever changing as new LLMs are being developed regularly, as well as different techniques for creating images. Obviously, many more experiments must be performed with many other datasets to see if these results hold in general, but for now, it seems that a picture is indeed worth 1,000 words. Next, I will hand it over to Krishna, and he will talk about some of the business implications.
Thank you, Pat, for indeed showing us that uh, image is worth 1,000 words. So, while this is very interesting, a question that comes to mind is why should a lending organization care about it? How does this impact their operations? So, let us start by talking about the most obvious application and the lowest hanging fruit in front of us. That is enhancing the tabular models that are already available to us. So, you know, um, to build a credit risk model, we use features or predictors which help us get to a score. And to bring the features to their maximum potential, we do what is called feature engineering, where we eh, make them interact, transform uh, them, and do various manipulations to select the right features and bring them and massage them into the right shape. So, uh, at the very least, we can take vision models as an additional tool for this exercise. Using this, we could get embeddings, mm, we could, in fact, get vision model scores or classifications, and there are lots of other ways in which our tabular data can be enhanced using vision model outputs, which will lead to a superior scorecard. And the great thing about this is that these models are fairly easy to implement within the local environment. So what that means is that data is not exposed to the cloud, and a lot of data privacy and security concerns are taken care of. And because of that, this becomes a very practical business innovation, almost a first step, if you will, where you can deploy vision models within your environment and use them to enhance your already existing credit risk scorecards. Another way in which organizations can use vision model is by actually using the images in their credit risk process and building multimodal models that use both the image and the traditional tabular data. So in doing so, uh, this could be, for example, for consumers, it could be their houses, or if we are doing B2B, these could be the offices, or if we are doing equipment finance, it could be the equipment against which the loan is being issued. In all these cases, this additional data will improve the model's accuracy. But the accuracy is not the only thing we are gaining here. We are introducing a new data source, a diverse data source, and in doing so, we are complementing the financial metrics. And because of that, our model will become more robust and stable, and we will have greater confidence in the applicant's credit worthiness. We are doing some experiments on this, and our initial findings are very encouraging. We will be hosting a webinar on this topic in December, and we look forward to having you there. We have till now talked about the approval process for a credit applications. But what about after the loan has been granted and funded? At this point, we still want to monitor our lendees to make sure we do not have a risk of default. Um, so, traditional approach here is to look for mispayments or signs of distress like uh, drop in scores, all of which is essential and excellent measure, but unfortunately, these are lagging indicators, not leading indicators of distress, and often too late. And over here, visual data provides us a big opportunity to speed up our action. For example, what if this was a retail store and we could get satellite pictures of its parking lot, say every Saturday, and we monitor it, and a sustained uh, drop in intensity of traffic there tells us something about upcoming financial distress. Or take an individual borrower, and if we could scan property images, any sign of uh, upkeep, drop in upkeep, lack of maintenance could be an indicator of upcoming financial distress. So these are just examples, but just just imagine how much additional benefit and tools an organization can get by using visual data to enhance their risk management. The next example I want to discuss comes from the leasing industry. Here, at the end of the term, the equipment has to be returned and its residual value needs to be determined. Now, vision models can play a very useful role here, that of the gatekeeper. Uh, Say, for example, the vision model replaces the first cut physical inspection of the equipment, and using the model, score is created, and those that pass the threshold of the score are not flagged for physical inspection and passed on to the next stage, but those which do not meet that threshold are put on physical inspection. This will lead to significant operational efficiency for the organization, cost savings, as well as time saving.